All right. So first of all, this is a 8-week class, right? And we have a lot of crap to cover in 8 weeks. So each week, your homework assignments are going to be insane. So there'll be a lot of work in here. Okay, so a couple things. First of all, let's kind of set up some ground rules. The course should be unlocked now, right? I think it's on Blackboard. You can see all the crap. I think I have the first week's assignments already up, and we'll start going through some of that stuff today. But so ground rules. Let's talk about some of this crap. Okay, so every week you will have a program and a paper. All right, so that's every single week. You're gonna have a program and a paper for well, actually, I guess for 7 weeks you'll have a program and a paper. Last week you'll have a final exam. Okay, so last week we'll have a written final exam. Okay, and sometimes I've done it where the final exam is a smaller in-class exam, and then there's a take-home portion as well, but it kind of just depends on my mood, I guess, but some sort of final exam type thing. Okay, so every single assignment are weighted equally. All right, so 100 points per assignment. Whatever you get on it, you get on it. Some important things that you need to remember for each assignment. Every assignment requires the self-assessment. So on Blackboard, I have a little document that has some questions for you to answer. These questions are like, what works, what doesn't work, how much time did you spend on the assignment, what grade would you give yourself based on your effort, what grade would you give yourself based on your result, and then what things you had trouble with. It's your opportunity to kind of tell me about your experience. Now, what's interesting here is a lot of times this is, and I want these for both programs and papers. That way, if your program isn't completely working, I kind of know where to go and look and kind of see what you were doing. So whenever you turn in an assignment, I need this self-assessment as well as the assignment submitted. So I'm using this thing for partial credit, but I also want it for the papers. And that becomes kind of extra important in our classes in here because I'm just looking around, I'll go out on a limb and say, none of you have English as your first language, right? Okay, so writing papers is going to be the more difficult part for you in here. Unfortunately, for accreditation, I say unfortunately, it's probably fortunate, but for accreditation, we have to have lots of writing in the classes. So, and that's going to be problematic. All right, so I want you to tell me about your research experience, what you were doing on that particular paper, what resources you used when you went and looked stuff up. You know, give me as much information as you can give me that will help me see the good stuff in your paper. Okay? Beyond that, I highly, 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 highly encourage you to visit the Writing Center for each assignment. So, one thing I will take off points for is if I read your homework and it reads like broken English, you know, that's not worth full credit regardless of content. Okay? So, I understand that is a challenge for some of you, but also understand that you're going to a school in the middle of Wisconsin. Okay? So, it's, you know, if, I don't think you'd expect me to speak you know, Hindi or Urdu or something like that very well if I were over there. So, but unfortunately, this is a graded type situation. So I do encourage you to go to the Writing Center. My experience has been that students who go and have their paper looked at by the Writing Center typically score about 20% better on every paper. All right? Because they'll look at your paper first. They'll tell you what parts sound completely stupid. They'll help you fix it. Then you submit it and you get a decent grade. All right, so do yourself a favor and go to the writing center for every one of your papers. Just write it first, have them take a look at it, then submit it to me. That way you don't have to come back and say, well, why did I get a 60% on this that looks like a 5-year-old wrote it or something like that. Okay? All right. Last ground rule. All programs are to be written using only the tools we have introduced in class. And I'm not just talking about the programming IDEs and stuff like that. We're going to use Eclipse in here, but I'm also talking about the API stuff. So, for instance, today we're going to start talking about linked lists. Some of you maybe have had linked lists before. Some of you are used to using the linked list built-in class in Java. We're not going to use the built-in linked list class in Java. We're going to write our own in here. Okay, so when I go and look at your homework, I don't want you to see, I don't want to see you using a whole bunch of built-in classes that do a lot of the hard work for you. It's not that I'm trying to punish you, it's that the assignments are geared towards learning a skill. Okay, so if you've had all these other things before, use what we've done in class to solve the problem. A TV show called MacGyver, every single problem we solve as human beings, we have to solve in terms of the tools we have laying around. So if you ever saw MacGyver, the guy would be like trapped in a garage or something like that, and he'd build an airplane out of a lawnmower and an empty 2-liter bottle of soda or something like that. All right, so every one of your assignments you have to solve in terms of the stuff we've introduced in class. Usually what will happen is I'll give you an assignment. It'll be hard to write the way I've asked you to write it. Then we'll solve it. Then I'll show you here's a better way. I'll introduce a new tool for you. And now that's in your toolbox that you can use for the next assignment. Kind of make sense? All right, so... and the reason I put that under ground rules here, it's pretty common that what will happen is somebody, I almost guarantee one of you who's not paying attention right now, is going to submit your first programming assignment. You're going to have all this garbage in it, stuff that we haven't introduced in class. So it's whether or not you wrote it yourself and are operating off some sort of back knowledge that you already had, or you went and found it on the internet. Either way, I'm going to give you a crappy grade on it because you didn't solve the problem in terms of what you wrote in class. All right, that makes sense? So don't try to get flowery. I'm not going to be impressed by you using classes that we haven't introduced. If you've had a bunch of programming experience, the class should not be too difficult for you. Just use the tools we've introduced, cruise through it, and be done with it. Okay? If you haven't had a lot of programming experience, trust that I've been teaching programming for 17 years. So there's usually a method to my madness. All right? You'll come out better doing things my way than, well, certainly than copying off the internet, but whatever. Okay. So, questions about any of that? So this covers all of our first conversation. When you turn something in that I don't like and I give you a bad grade on it, then you come and beg to redo it. I'm going to say no. All right? We've all covered that now? All right. I think, has everybody in here had me before? Okay. I'm not as nice as some of the other guys. I'm funnier. A whole lot funnier. Okay. But, yeah, I'm not really a pushover. So it's, you're all adults. Just deal. Okay. So every assignment is graded equal. The final exam is worth 20%. So, relatively small piece of your final grade, but big enough to matter. All right, final exam will be a large amount of programming on it, handwritten. Possibly, I'll take us down to the lab if we can get it, but I wouldn't bank on that. It'll probably be a handwritten exam. Usually, I design the finals to last I usually do like an exam that you should be able to complete in an hour, and I give you 2 hours to work on it. It won't be a 4-hour exam. I'm not sitting here for 4 hours, so I wouldn't expect you to either. Okay, so questions about any of that stuff? All right, so let's kind of dive in and let's talk about what this course is about. So this is 537, which is our second programming course in the MSIT major, right? So, things are a little funky in our major here. So we had a master's of IT before we had a master's of computer science. Our master's of computer science is starting here in the fall. So we're starting that up. My PhD is in computer science. So that's why I teach our more computer science focused courses. So this is going to be taught like a computer science based data structures and algorithms course. So, we have this idea of, let's talk about data structures first. All right, so the prerequisite for this course was 535 or 835, whichever one, if you took the online version. So that was kind of programming one, like what is programming? We introduced Java, basic programming concepts, loops, things like that. And just as a quick little review, something I always talk about in there that kind of becomes the foundation for how I teach programming is this idea of how humans solve problems. All right, so I say that human beings solve problems by using their memory, asking questions. That was weird. And repetition. All right. So that's how human beings start off by solving problems. And you've probably seen on our website the computer science thing says we solve problems. That's stupid, isn't it? That's not like an impressive saying. We solve problems. That's very boring, right? Yeah, but it's very boring to brag about that. Yeah, I think we should have like dragons and explosions on our homepage. Be way better. All right, so this is how human beings solve problems. Now we want to talk about what's the goal of a programming language. And again, these are all things that I talked about in the previous course, but let's just get us back in the programming mood here. So programming languages, for a starting point, the job is to allow us to tell a computer what to do. Simple enough, right? All right, take it a step further. These guys try to allow us to work with computers in a way that is similar to how we already solve problems. All right, so this is what I always kind of advertise as the challenge for programming. Now, out of curiosity, how many of you in here have had programming outside of 535, or would you consider yourself relatively experienced programmers? A couple of you? I know this is Blade, by the way. You guys might know him by other names, but yeah, he comes to our programming competitions. So he was on our hackathon teams, and he's part of a startup company that we're working on in the department too. So he's done quite a bit of stuff. So we'll kind of throw this out there. The punchline for the perception is typically that computer programming is hard. Okay, that's kind of a starting perception we might have. The problem is that it's not the languages that are hard. It's human beings are so good at solving problems. Every one of us in here we're really, really, really good at solving problems. We're so good, in fact, that we have trouble articulating how we solve problems. All right, so let's see, sports in here. We probably have a bunch of soccer fans, right? Cricket, who's a cricket fan? Any other made-up sports that we're fans of? Who's an NFL fan? I know you're an NBA fan. Yeah, basketball fan. Packers fan, that's extra credit. Yeah, I know. I was just in Denver this past weekend where the Packers are playing this coming Sunday. I took a picture in front of the Mile High Stadium. This was a threat. Get off the tracks when the train's coming through, right?
You wear the Packers hat?
I have my Packers hat on.
There's no doubt that you will get up.
Okay, so the idea here is that human beings were so good at solving problems that we have trouble articulating how we solve them. So let's take soccer as an example. All right, so if so anybody in here a relatively experienced soccer player? I'm not saying you're playing professionally, but you consider yourself a decent soccer player? Decent? You're a decent soccer player over there? Okay, so now I'm a complete beginner. I don't know anything about soccer. So I'm going to ask you to teach me how to do one of those curvy kick things. When the guy runs up and the kick goes flying around people and then flies into the back of the net, and then the guy's screaming on the TV, and I'm talking about all that stuff. All right. Okay? Now, you've done kicks like that, so fine. You're not a professional. You're not as good as the crazy guys on TV, but you're a lot better than I am, right? Okay? So you've done that so many times that it becomes somewhat second nature to you, correct? You would struggle trying to teach me how to do it. Okay? You can academically understand something. So you could academically teach me how to kick the kick, how do you angle your foot, because some of those kicks you kick with the outside of your foot too, right? Yeah, there's all sorts of things that you're like fumbling over your own feet, right? So you can academically teach me how to do something, but until I've practiced it, I've kicked 1,000 times or 5,000 times, whatever it is, it's not going to be something that I can just do in real time. Okay, where you watch these professional athletes running around the soccer pitch. Is that what it is? The soccer pitch. Ha, nailed it. I think it's what it's called. You didn't know you're not a soccer fan? You're a cricket guy?
I told you, Packers.
Packers? Oh. Well, you weren't born here, right? You were born over there.
No.
So you didn't even know about the Packers when you were over there.
No. But I didn't like football even there.
Really? So you were like an outcast. You Saudi or Indian?
My dad is from Middle East. My mom's from Greece.
Oh my gosh, that's awesome.
Everywhere.
So you're from all of it. You're like a hodgepodge.
Yeah, I lived in Asia, Africa, Europe.
Really? Yeah. How many languages do you know? Just two? So you just didn't talk in some of those places?
I mean English.
Or you just fall back on English?
Yeah, English is more than enough in some countries. The second language is enough. That's all I need.
I gotcha. All right, so the idea here is that we can academically learn something, but until we have practiced it a zillion times, we can't just do it, right? All right, so that's the issue with learning programming. This isn't something you can just go home and study and come in and be ready to go. You can't teach me the 5 different soccer moves and tomorrow I'm not trying out for a professional soccer team, right? I'm not going to have that skill set probably ever, but certainly not by tomorrow. Okay? Same thing's true with programming languages. I want you to think about them much like a sport. Okay? There are going to be aspects when I do something on the board here, it's going to make sense to you, but when you have to go home and do it on your own, it's not going to come as easily. Right? Just like if I had to watch you kick that kick 10 times and like, oh, you make it look so easy, right? I go out there and I'm stumbling over the place, I'm kicking and whiffing, right? Yeah, I mean, when you got to kick on the outside of the foot, I'm going to break my ankle. I'm not built for that. I'm like more built for like fishing.
I would rather be more like with golf.
Or golf. Yeah, golf doesn't require as much foot motion. There's a lower chance of falling over. Big chance of whiffing, but not falling over. All right, so in any case, think about programming as a sport. And understand that our programming languages are the tool that we use to talk to a computer, to tell a computer what to do. All right, so think about this like in your sports, soccer, we have specialized shoes and things like that allow us to run at full speed on possible wet grass and stuff like that, and not fall over the place. So these are power tools that we use that make our life easier so we can focus on the game of soccer. Okay, things like that. Programming languages are the same thing. I want you to think about, and here we're going to use Java as an example language. We're using that for kind of 2 reasons. One is it's a good teaching language because I don't have to worry about what kind of machine you guys have. So if you have a Mac or a PC or a Linux box at home, the stuff we're using in here will work just fine. It also gives us an advantage where the second, not quite the second half, but about the last third of the class, we start looking at some of the stuff we've talked about in the context of Android programming. So again, maybe I would prefer to do it in iOS programming, but not all of you have Macs. I'm sure not all of you want to come into the lab down here to work. So again, Android programming makes it so that it doesn't matter what kind of machine you have, we can all do it. Okay? So no harm, no foul, and it allows us to kind of explore something that is going to be a little bit more in the business world. And I think we can certainly look forward and see that, when you guys get out there in the industry and you start working in IT, you're going to be working with mobile stuff more and more and more every year, right? That's certainly the future. It's already the now, but that's where we're going. Okay, so our programming languages are our power tool. I don't want you to treat them as something where we have to meet the computer halfway. The programming language tries to come most of the way towards us so that we can talk to this alien being that is the computer. All right. So our programming languages are our power tools that try to harness the way that we already solve problems so that we can tell the computer what to do. All right. And again, our weakness as human beings is we are so good at solving problems that we have trouble articulating how we solve them. Okay. As good as he might be at soccer, he would still struggle teaching me all the little tiny nuances of that kick. Okay, because there's things that he learned about years ago that he doesn't even think about anymore. It's so second nature. All right, all of us in here, when we walk, when you were a little baby and you were learning how to walk and you were falling over every 2 seconds, there was a lot of things that you were keeping track of. Things that we've forgotten now, right? We don't think about it. When you're walking down the hall, you're not like worried that you're going to topple over. There's 5,000 things that are going on just to take a step, all the little muscles you're contracting and stuff like that. We aren't capable of telling somebody like, oh, what you need to do is you need to have your brain send the signal down your back to your calf muscle and it's going to contract. And that's when, at that exact moments when you're going to shift your weight. Okay, but don't shift it too much, just a little bit. Okay? There's a level of detail that we all know exists with walking. Right? But we lack the skill set to articulate it because it's so second nature for us. All right? That's why programming is difficult. Not because the languages are hard, not because talking to computers is hard. It's because we're too good at solving problems. All right? Human beings are operating at this whole other level. All right? A lot of us, we think that this idea of our video games, let's take a video game as an example. I assume we're all gamers in here, right? Okay, Battlefield? Who plays Battlefield? Battlefield? Okay, so Battlefield, really cool game, right? Explosions everywhere. There's a zillion things happening on the screen, all this jazz, right? Okay. Would you imagine that writing Battlefield, if you were the programmer who wrote Battlefield, that would be really, really difficult? Okay. Writing the entire game Battlefield is absolutely trivial compared to walking down the hall. We don't have that perception because we understand walking, right? That's commonplace for us. Nothing gets exciting about walking. Okay? But what does it take to build a video game with all those explosions and stuff like that? That seems so far beyond us. When the reality is that that's such a smaller problem than just walking. Making things show up on the screen and spin around and certain things impacting with other things. It's such a smaller problem than walking. But we don't perceive it that way. We immediately assume that doing something like that is very difficult. Does that make sense? Okay.
It reminds me of the hoverboard. When the first time I was standing on the hoverboard, I just realized how it seemed like I was trying to learn how to walk.
Yep.
So it's kind of tricky.
There's
so many muscle memories.
Yeah.
Knowledge in order to control your body to have balance on that hoverboard.
Yeah, I should bring that in. We should get everybody on it because that actually is a decent analogy. So the department has, I guess we call it a hoverboard. It's a self-balancing board, like a Segway without the handles. Yeah. So when you first get on this thing, you don't trust it. So you basically, you're sitting there just wobbling all over the place and stuff like that. Right. But then once you get used to it, like I have it at my house right now. I just ride it. I have hardwood floors. I just ride it around my living room. I do spins and stuff like that. I'm checking email and stuff while I'm on it. It's become second nature for me. It's real easy. Okay, but it's that type of thing that things that we perceive are easy aren't necessarily as easy as we perceive them to be. Right? Like we said, walking down the hall, I think last semester when I first introduced this, I probably said something like, how many of you got to class today without bumping into any walls? Something like that. And most of us are walking down the hall, checking our email or sending texts, things like that, right? It's not worth our time to look in front of us, okay? It's such an easy problem for us to solve that we're not even going to look in front of us. Yet let's look at like robotics. We don't have robots that are just walking all over the place. Just the act of walking or going up a flight of stairs or down a flight of stairs is really difficult. Yet we don't even pay attention when we're doing it. Okay, so kind of flip your mentality over when we're getting into some deeper programming stuff here, and understand that we're not trying to learn something hard. We're trying to train ourselves to think more simplistically because we're used to operating at such a complex level as humans. Okay? So, in any ways, programming languages, these are a power tool that we use that's provided to us by somebody, whoever made the language, that we use to talk to this dumb alien computer. Okay, so that we don't have to drop down and think in zeros and ones. Instead, we can think as close to the way a human being thinks as possible and tell this thing what to do. Okay? And again, here's how human beings already solve problems. All right, so that the matchup slide there, I usually call this guy the mapping, if you remember that. Every single programming language will have facilities for these three things. Memory, it does through variables. Asking questions through conditionals, usually if statements. If statements. I'm way better at programming than I am in English, trust me. All right, repetition, this is loops as well as methods, functions, however you want to reference it. 100% of programming languages will have facilities for those three things. Okay, this is the way human beings already solve problems. A language like Java is going to give us facilities for emulating these three things. So now we can, as long as we don't get too intimidated by trying to solve problems, we can now tell a computer what to do. Okay? I can put any brand new language in front of you you've never seen before, and if I can teach you how to define variables, ask questions, and do some repetition, you can already solve a pretty large classification of problems in that brand new language. Okay? So, having said that, one mentality I want to remind you about. Mentality, is that a word? Yep, there it is. Programming is programming. The language does not matter. All right? So, throw away this idea that, oh, I know Java but not C++, or I understand C#, but Objective-C is, I'm not good at that, stuff like that. All programming languages are identical. Every single one of them. All right? It's a perfect example in a classroom like this, much easier than when I'm teaching my undergrads. As you've already seen, in technology, in the United States, undergraduate programs are almost primarily American, right? But graduate programs are almost always predominantly non-American. That's not just here. When I did my PhD and my master's degree, I was a minority in the program. That was in Illinois, University of Illinois. So it's very, very common. Other countries are far more, I guess, motivated to get higher education in technology. I think Americans kind of sit on their laurels, or whatever that means. Why does this keep flipping back and forth? It's very weird. iCloud must be doing something funky. Okay, so in any case, programming is programming. The language doesn't matter. So what we're learning in here is the computer programming skill set that we can then apply to anything. When you guys go out into the IT world and you're doing server management or something like that, you're going to take this computer programming skill set and you're going to apply it to doing automated backups, creating user accounts, doing all sorts of other things, moving information around. And having this skill set is going to make it so that you have to do less individual labor to pull things off. Okay? You're going to be that person that can write scripts that automate part of your job. Okay? For those of you who are going to be bet more on the computer science side of things, doing software development, that kind of stuff, this is the tool of the trade, right? Okay? You wouldn't walk onto a soccer field without any sort of soccer skills. All right, so, but again, the mentality here is that we're learning programming as a skill set. We're not learning Java. We're not learning C#. We're not learning Android programming, whatever it is. It's programming as a skill set, and then you can go and learn any other technology pretty easily. Okay? So, kind of keep this in mind. Programming is programming. The language does not matter. It's like a sport, that kind of stuff. Put this stuff in perspective. Okay. Now, have any of you ever had a data structures class before? Or something that was called data structures?
I think
Hey, what do you, huh?
Imaginary class.
Okay. And so tell me about this class. What language did you use, and what do you think a data structure is?
Actually, I did my bachelor's in electronics. So there was a class in database management systems. So I guess there was data structures in that particular subject.
Okay. So what is a data structure? What would you say a data structure is based on the class you had?
Data structure contains the stuff from the things like it's like a flow chart for a particular thing to run.
Okay. Yeah, I kind of like the flowchart analogy. One thing I like to kind of focus on is in technology, we like coming up with kind of big formal words that mean easy things. Okay, so for instance, how many of you have heard of something called a design pattern?
I'm reading the book.
Okay. You're reading a book called Design Patterns? Oh, that just sounds completely boring.
Yeah, it's really boring, but it's quite.
Now, most of us are in technology, so at some point, you've probably, at least in passing, heard the phrase design pattern, right? At some point, right? And most of you maybe don't necessarily know what it is, which is actually most people. Even people in industry, design patterns, this phrase gets thrown around all the time, and the assumption is it's this really formal thing that's above us or something like that. Anybody know what a design pattern is? What that generalistic phrase means?
Kind of generalized ways to do things efficiently.
Okay. Efficiently is probably still giving it too much credit. But I think that's pretty much correct. So, if I were to give a definition for design patterns, go ahead. I like to dumb it down too.
Solutions for any software design problems, any software related problems.
Okay.
Solutions for that.
Okay. So, taking solutions to even a more generic step, let's say something like,
which are mostly like reusable and many ways for many problems.
yeah. So let's say it's best practices for solving common problems.
Yeah.
Okay. Where a common problem can literally be anything. Right? If you are a rocket scientist or you're working at Lockheed Martin building missiles, common problems for you might be fuel consumption type issues, where common problems for somebody who writes video games probably has little to do with fuel consumption. All right, that kind of stuff. So this idea of common problems is kind of all over the place. Design patterns, I really think this was invented by academics, this word, because it's our go-to move for getting easy publications. All right, so let's say I need to have a publication. So I got a PhD. We're supposed to, you're supposed to write papers and get them published and that kind of crap, right? So I just got to pick some problem that I'm interested in solving, propose a solution to that problem, whether it's good or not. Okay? It doesn't matter whether it's a good solution or not, just a solution that I'm proposing. I'm putting it forward as a possible good solution. And then the kicker is you always have to come up with a weird name. Okay? All design patterns have weird names. Every one of them. All right, so weird name, some common problem, a proposed solution, slap that together in a paper, it gets instantly published. What's the worst that happens? Somebody else says, oh, I have a better way of solving that same problem. Oh, you're right, you do. Check, publication. Okay, so there's literally a zillion, I'm rounding down, design patterns out there. Okay? Now the reality is, a couple of design patterns have kind of floated to the surface as being popular, right? So some of them you maybe have heard of, whether you know what they are or not. One of them is MVC. Another one is the Observer. Another one is the Singleton. So these are kind of three famous ones. And so these are all kind of weird names, right? Especially Singleton. That just seems like it must be really, really difficult.
Yes.
All right. Doesn't that sound like it? Just it's hard, right? Anybody in here know what the Singleton design pattern is? Besides Blake, because I taught it to him. Must be difficult, right?
No, it's not. Not at all.
Singleton design pattern says it's a good idea to store things that need to be shared between multiple, let's just say in this world, objects in one place. So, real life example, let's say every one of us in here, we're sharing a car. And we're going to pick this one drawer over here. That's where we're going to keep the keys. If any of you need to use the car, you don't come to me. You don't go to Blade. Go to anybody else. Go and check the drawer. The keys are there. Car's yours. Make sense? That's the singleton. Put shared crap in one place. Get it? Singleton, single place. Haha. That's singleton. All right. Well, and we'll look at it in here as well. MVC. Oh, this is a famous one. Anybody know what MVC stands for? Model View Controller. Well, that doesn't make it any better. And now you've just spelled out MVC, so Model View Controller still sounds just as complex, right? Okay, what does MVC mean? Good idea to separate your logic from your design. When you're creating an application, have your interface design in one place, have your code that makes it work in another place. Don't put them in the same file. That's MVC. Simple concept, right? Okay. Fancy name, sounds a lot harder. All right. Oh, observer. This is a great one. Okay, observer. It's a good idea to not wait for an event to happen, rather be notified. All right. So let's say that we get you on that hoverboard for the first time, and we're all just waiting for you to fall. Okay, it's gonna happen. Well, it won't. I'm bigger than you. So I'll hold on to you. That was actually a skill I had to learn when I was teaching people to get on this hoverboard. I had to practice with my wife because, I mean, when you're helping male students get on this thing, it's one thing, but you have to be careful where you're grabbing, well, really grabbing anybody, but, you know, in any case, I won't let you fall is what I'm saying. All right, so, but punchline is, so it's a good, so the real life example would be, we're all interested in you falling, okay? But we also want to be productive. So we can put you on this hoverboard, we can all stand here and just gawk, just waiting for the inevitable. Did he fall yet? Did he fall yet? Did he fall yet? Did he fall yet? But we're not doing anything else, right? There's all this stuff we could be working on during all this time when you're not falling, okay? But as soon as you fall, we want to know about it, okay? So your job is when you fall, we want you to scream, okay? I mean, a real terrifying one too. You know, we want to notice. So we're all going to be off doing our own thing and stuff like that. And all of a sudden we hear his scream, and that's when we look over and pay attention. All right, so we were able to be productive doing other things, but we still didn't miss the fall. Make sense? That's the observer design pattern. Don't waste time standing around looking. I'll let you know when there's something to see. That's observer. Okay? Now, that's just a list of 3 there that we've talked about. So we can imagine these are popular ones. There's a zillion other ones out there that have really crazy names that are not popular. Okay, these are the ones that have kind of bubbled to the top. Okay, so design patterns are a perfect example of kind of one of the ways I like to look at technology, where we keep trying to come up with fancy names that make us intimidated. Okay, we think that things are difficult. Even in our world today, when you go out and you get an IT job, whether you're supporting the hardware and the software in the back end, or you're writing the software on the front end, you know, different technologies you're going to be working with. So, you know, just kind of throwing a bunch of tech stuff out there. We have, you know, PHP, we have Ruby on Rails, we have Python on Flask, we have Node.js, we have Agile, we have Angular, you know, so on and so forth, Ajax, jQuery, you know, we can just keep making a list after list after list after list. All of these are very similar in what they do. They just have funky names. All right, new cool kid is Node.js. Oh no, actually, then we have React. React, that's a Twitter, Facebook collaboration. Yeah, React, that's a technology for making websites pretty. Yeah. Oh, then Bootstrap. Yeah, that's another tool for making websites pretty. They're all the same. These things are all the same. It's no different than Toyota versus Chevy versus Ford. Okay? Now, sure, innovations happen, right? So like, right, you know, if we were going to look at like Node.js or React or something like that, one of these kind of newer technologies, we might compare that to like Tesla, the new Tesla cars that do the self-driving stuff, right? So there's still a car, right? Any one of us, well, I say any one of us, I might have a little trouble fitting in some of the Teslas. I've got a technique. I crawl in head first, kind of put it on like a shirt, okay? Once I'm in, I'm good. Okay, I fit in it, it's more like, that's a height thing. But, you know, Teslas, so they're a car just like any other car. We could all sit there and drive a Tesla, but they have some new innovative stuff, right? That's kind of Tesla's thing right now. They keep coming out with cool stuff. So now we have cars that are driving themselves on the interstates and things like that, which is fascinating, right? But if you're trying to bring in some analogies here, think of Teslas and their kind of innovative stuff as being kind of like some of these new technologies, Node.js or React or something like that. It's still a car, okay? Still has to get fuel somewhere, whether it's electricity or gasoline or, you know, whatever the alternatives are, vegetable oil and all this other stuff, you know. It's a car. It just does two or three cool things, right? That are a little bit newer, a little bit more innovative, stuff like that. So don't get too intimidated in technology when we're already kind of desensitized to it in real life. We all think the Tesla thing's kind of cool, but we're not like dying of jealousy thinking about Tesla because we're used to new technologies coming out all the time. But when it's like shrouded in mystery underneath these names, you know, jQuery and Ajax and Bootstrap, these are like, oh, what the hell is that, right? It just sounds crazy, right? It's easy for us to get intimidated over nothing, all right? So try to keep that perspective. So again, that's a mentality thing that we want to keep, all right? Okay, so talked about design patterns, kind of demystified that a little bit. Let's talk about data structures. All right, so data structures are structures for holding data. Just intriguing when you just rewrite it, right? Okay, well, what does that mean? Well, in real life, a majority of us in here are guys, so we're probably mostly slobs, okay? But hopefully we have some level of organization, right?
So you go back to the shoe box.
Yeah, so in real life, so in my house, I have a shoe bench right inside the door. Not my idea. Yeah, I married an organized person. Okay, so my wife has a shoe bench. I get yelled at. I'm only allowed to have one pair of shoes outside of the shoe bench. Well, actually, I'm allowed two during the summer. I get my Crocs and my normal shoes. Okay, any more than that, I'm in trouble. All right, but we don't need a shoe bench to store shoes, correct? I can just come in and throw my shoes on the floor, no harm, no foul. Okay, but having them in the shoe bench keeps them organized, keeps them in one place, makes it easy to get the left and right shoe. There's advantages to that, right? So that shoe bench is a data structure for shoes. All right? Data structures are just organized tools for holding things. Whenever we write software, we're almost always working with data in some capacity. Okay? We're holding pieces of information, we're passing it from here to here to here to here, we're changing it, we're manipulating it, we're adding to it, we're removing from it. These are all things that we're doing with data. Okay, so a large percentage of computer programming deals with data manipulation. All right, now the basic structures that we have built into our languages allow us to do some common things. So we have strings. Right? Strings are what? Collections of characters inside of double quotes, and we can do certain things with strings. We can get a character from a certain position. We can add something to, we can concatenate strings together, for example. We can look up for where the position of a character is. So they have some abilities, right? Just like my shoe bench has some simple abilities, but they still have limits. As the type of data we're trying to hold becomes more complex, or the types of operations we need to work with that we want to apply to that data becomes more complex, the structure in which the data needs to be organized probably needs to become more complex Otherwise, we're not going to be very efficient. Okay, so let's take this again away from technology. So let's say that you are you're building something in your garage. Okay, building a shed or something like that. Okay, and you have a bunch of tools. Are you going to be able to work more efficiently if your tools are kind of organized? You have, the wrenches in one place and the screwdrivers in other places, opposed to you just have this bag of tools. Okay? Inside of this garbage bag filled with 5,000 tools is everything I might need. All right, and then and then you need the socket, the right size socket. I know there's about 300 of them in there. Okay. I have 2 of these. One of them's really rusty. The other one's not. They're somewhere in the bag. Okay. Now, could we still solve that problem? Sure. Eventually. Right? Yeah. But it's not an efficient way of solving the problem. Not because, and that's one thing I kind of want to throw out. That's something that Blade said here a little bit ago with the design patterns is don't always strive to come up with, quote, optimal solutions to everything. We want correct solutions first. Then we can turn around and try to optimize solutions that need to be optimized. So one thing we want to keep in mind when we're dealing with computers is computers are really fast. Really fast. And the majority of the problems that we try to solve, a majority of them, we could solve it in the absolute worst correct way possible. And it wouldn't feel any faster or slower than if we solved it in the best correct way possible. That's for most problems. Okay? So don't spend all your time coming up with these optimal, I reinvented math and came up with this solution that balances the universe and all this stuff. And in the end, it spits out a Pop-Tart. All right, so when you could have just put it in a toaster and pushed the button, and 3 minutes later you got a Pop-Tart, right? Okay, so don't overcomplicate things just to overcomplicate things. And this is kind of where things bleed over a little bit into the IT world. So, out of curiosity from this group, how many of you are going into your typical IT industry doing hardware management, server support, things like that? How many of you are interested in going that direction?
I do that.
Okay. How many of you are interested in going more on the software side of things? So writing software, doing whether it's software design or a data analyst where you're designing solutions and letting somebody else write it, but that kind of stuff. Okay, and the rest of you just here for the student visas? We got like 3 hands up, 3.5 hands up. Yeah, there's probably more truth to that than it is really funny just how travel and stuff works because, a lot of people from all these foreign countries want to come over here and study, where a lot of Americans want to go overseas and travel. And, like I'd love to go to China. Blade just wants to get out of China. You see what I'm saying? It's very interesting. I'm going to this June. I'm going to Israel and Egypt. With our church. So we're doing this whole Holy Land dealy flippy, and
Which church you go?
Beautiful Savior. It's Lutheran here, and I was born Jewish, but I'm not going to tell them that in Palestine and those places. I converted when I was in high school, but what's funny is there's a lot of like dangerous stuff happening in Egypt right now, right? My wife's not concerned about that. She's not concerned about the bombs or the sand pirates. She's concerned about the squat toilets. Yeah, apparently every other weekend there's tour buses that are getting taken over by sand pirates. So I might get to spend a week in like at a sand pirate death camp or something like that. That would make I don't want to die, but it'd be kind of a cool trip, like a story, right? No, she's not even concerned about that at all. It's, oh no, not the squat toilets. So we've been asking Blade for tips. So I don't know. I thought that was funny. All right, so, in real life, we like to organize stuff in such a way that it's easier for us to work with, right? Same thing is true in programs. Okay? As our problems that we're solving get more and more complex, the nature of the data gets more complex, or the nature and the way we're using the data gets more and more complex, it will be in our best interest to organize that in interesting ways, spending our time organizing ahead of time so that when we actually need to use it, daily problem solving, it's in a good format for us to work with. The tools are in their toolboxes, they're labeled, things like that, as opposed to in the garbage bag. Okay? We'd like to spend a little extra time keeping our tools organized because it'll make our life easier every single time we need to use those tools. Okay? That's the purpose of data structures. All right? Now, kind of an important thing with data structures, though, and this kind of falls into the same category as this design pattern thing, is there are some famous data structures, and then there are all the rest of the data structures. Okay? So when you go out and you look at a book on data structures, you get a some old dusty computer science book that talks about data structures. They're gonna list the common ones. We got linked lists, we have stacks, we have queues, we have trees, a whole bunch of different kinds of trees.
Yeah.
Tons of trees. Then we have graphs. We got some new ones. These weren't in the old books. These are in the new old books. We have things called bags.
What is that?
That's just a made-up thing, right? It's like, well, I mean, in real life, we have a bag we throw crap into, and sometimes we grab stuff out of the bag. Do we have to have an interesting way of getting stuff out of the bag? Well, sure. Well, let's put that inside of a data structure called a bag. It's nothing special. Just an object that they happen to call a bag. It has some rules associated with it. Things go in one way, things come out another way. All right. So, these are your common data structures that most books would throw around. Okay, but I'd argue that any object is a data structure. This includes the ones built into the languages and the ones we build to extend the languages. And this kind of goes down to this idea of object-oriented programming. Okay, and that's something we talk about in the previous class, but we talked about the evolution of C to C++ to Java to C#, all that crap, right? And one of the things we talked about when we went from C, which is a procedural language, to C++, let's kind of go back here. Let's recreate those slides real quick. So we talked about the evolution of C. And I like to look at C through the lens of a variable, okay, through our variable, remembering things. So C had variables. So that's a single name with a single value. C had arrays. That's a single name with a collection of like values. C had something called a struct, a data structure. Okay, it had a struct. Okay, structs were a single name associated with one or more named and not necessarily like data. Okay? So that's what a struct was back then. So we could create like a struct for a person. For example, it's usually kind of an example I like to use. So, we'll create a little sample struct here. So we're going to say struct person. And then we're going to say a person has a string name and an int age. All right, so those are the two pieces of information that we're going to keep track for a person. Okay, and then we can go ahead and create a person. So we can say person p, and then say p.name is equal to Mike, and p.age is equal to 15. Maybe a little older than that. but I still act like a 50. Actually, I probably act like a 7-year-old.
Probably like 15 is your
You think?
age. I guess so.
It could be. Have to ask my wife, see what the.
So what's your comment of the wife about your age?
But how old she acts?
No.
Oh, she's the mature one.
No, I mean how
Yeah.
she says your age. You act.
Oh, I assume like a kid, 5, 6, 7, and it probably goes back and forth between whether or not I'm even human or like a pet.
Just like your dad.
You know, when we go into like a mall or something like that, and it says no pets allowed, and she tells me I have to be on my best behavior. Yeah. Like I wad stuff up and throw it at people at church.
Really?
Yeah, I have problems. Who wants to grow up?
Alright,
That's true.
you are still in.
Yeah, I mean my classes might be hard and stuff like that, but I mean, isn't this as fun as you're going to have in a 4-hour class?
Absolutely.
I mean, they're bad any way you cut it, right? And by the way, this is an absolute horrible format for learning programming. So I've made this argument about how, it's all about the reps and treat it like a sport, and you can academically understand something, but then we have the trade-off of our program kind of caters to non-traditional students. Several of you are working professionals, right? You can't come to school at 10 in the morning, 3 days a week, or something like that. So is what it is. So work hard outside of class on this stuff because you're really getting the information in a very inconvenient format. 4 hours a pop for 8 weeks is not the way to learn programming. It is what it is, but consider yourself warned, I guess. Okay, well, in any case, this is a data structure. It's not one of our famous ones. It's not one of the dudes we talked about here. It's not a linked list or a stack or a queue or a tree or a graph or any of those guys. Okay, it's a person. You didn't find that in any of the textbooks. Okay, so this guy's a data structure. Why? It's a structure for holding information about this kind of thing. A person thing. Okay, a person has a name. They have an age. I guess they might have a height. There's all sorts of attributes we can say as a person. We can have another struct here. So maybe we have a struct called fraction. And this fraction maybe has an int numerator. Forgot my A, and that's not a. And an int denominator. That's a structure. That's a data structure. It's a nice little container that knows how to hold fraction stuff. Right? Just like my shoe bench at home. It's a data structure-y thing, right? It holds shoes. It also has a couple of drawers in it that I guess I'm supposed to put receipts in. I don't do that very good job of that. I get yelled at for that. I'm in charge of killing spiders and other flying insects. That's why my wife keeps me around, which kind of puts me in that category of a pet. That's why I don't think that's a far analogy. A couple of you are friends with my wife on Facebook. You can ask her.
Just like your cats may have the ability to catch mouse.
It's true. We don't have mouse problems in our house.
But you have
We're down to 2 cats. We had 3. Yeah, chances are you have that many cats, you probably aren't going to have a whole lot of mice. It's kind of like us traveling in like the Jurassic Park movies with the velociraptors. It's just not safe. Right? If you're a mouse, you probably don't come into my house. Although my big cat's pretty lazy. I don't know that she even chase a mouse anymore. She doesn't even play with the little laser pointer thing. She just sits there and looks at it. It's like, get it a little closer. Then you get it next to her. Her sister she'll go nuts. She'll chase that thing around for 45 minutes and she'll literally passes out from exhaustion. Okay, so in any case, these are structures. Data structures just like anything else. Okay, so again, throw this idea of traditional data structures that we're learning about linked lists and stacks and queues. We're going to learn about those things in here, but not because it's important to learn about stacks and queues and linked lists. We're going to learn about them is because they have tradition in terms of data structures, but when we say linked lists, this guy right here, and stacks and queues, all three of these are examples of linear linked data structures. That is how we're putting them together. Okay, so it's kind of a technique we're using for building a data structure. Okay, just like my shoe bench at home. I mean, I'm not a carpenter, but I'm sure where the things connect with each other, they had to use special techniques to make sure it was rigid, it was sturdy, right? Okay, and so every time we're going to build something like a linked list, like a stack, like a queue, or other linear things that need to kind of be memory efficient, we're going to go to this fallback move of building things that are linked together. Okay, and that's what we're going to talk about in terms of linked lists. So it's not so much that we're learning linked lists, we're using linked lists and stacks and queues as examples of things that we can use this linking technique for. Okay? So just like the technique for creating those hinges and wedges and all those things for the shoe bench, can be applied to other things other than just shoe benches. All right, so when we talk about the evolution of C, we had variables, we had arrays, we had structs. Okay, so built into a language from 1968. Okay, so structs C has been around longer than any of us. I'm pretty sure I'm the oldest in the room and it's been around longer than me. All right, so I think I'm the oldest in the room. I think probably. I've been teaching for 17 years. When I started, I was not the oldest in the room. So, in any case, C had some weaknesses. Okay, just like we've been talking about in here, as the types of problems get more complex, as the things that we want to do with the data that we're working with get more complex, we have to come up with evolutionary things to store that information, to work with that information. Every single week we're coming out with a new cool toy, whether it's a new iPhone or a new Android device or a new programming language technology. Like we had this big list back here with Ajax and jQuery, and just invent a bunch of syllables right next to each other, and it's probably going to be the name of something soon. Okay, just babble something. We just keep coming up with ways to make our lives easier, right? Okay, so the idea is that C was great for a time period, but then as our computers got more powerful and as we started solving more complex problems, we kind of needed a little bit more, let's say, powerful or more capable language. Okay, and that's where C++ came from. Well, let me actually steal this slide. So we say the evolution of C++, we kept variables, we kept arrays, we kept structs, but we added something called a class. Okay, what's a class? It's a struct with methods, functions, whatever you want to call them, procedures, pick your poison, subroutines. That's all a class was. Okay? We try to think about object-oriented languages as being this huge evolutionary step, and like, I'm really into OOP. That's what we see, right? OOP, object-oriented programming languages. Okay, object-oriented programming. All it is an organizational structure. A class in and of itself is a data structure. It's a data structure capable of holding pieces of information, attributes about something. Like we have our attributes about persons and our attributes about fractions here, as well as actions, methods, functions that can do stuff with them. Let's throw both of those into one container. Okay? Our TV sets at home have a tube. All right? And then what else do they have? They have some radio receivers because we want to be able to do stuff. I point the little remote because God forbid I have to get up and change a channel. Any of you remember TVs when you had to get up and change channels? Or have remotes always existed in your lifetime?
Yeah, in my child, I switched. They're still turning around.
Yeah, I remember the first remote. It's just amazing.
Yeah.
Like, wait a minute, I don't have to get up anymore? And we wonder why America's getting fatter. There's a couple comedians that do a thing on that. And I could talk about it as a fat person, so it's not offensive. But it's funny how we have like charts to measure like obesity levels, right?
Oh yeah, I read it.
And they keep changing the charts. So a person could literally be as fat as they were a year ago, but on the charts they're less fat. Instead of being morbidly obese, they're just obese. So rather than improve our health, we just change the chart. It's like, well, last year I was morbidly obese. Now I'm just obese. Not because I've lost. In fact, I've gained 15 pounds. They just changed the chart.
So is it because the reason why you do the extension belt?
Huh?
Because they changed the belt length.
No, I see. Actually, that's not true. That was a big deal. He's talking. I just got back from my trip, and I usually need a seatbelt extension on the planes. Okay, but I didn't this time. And actually, Southwest has a fairly old fleet of planes, so those older seats are smaller with even shorter seatbelts. So that was pretty impressive that I didn't need a seatbelt extension.
So it doesn't mean they also changed the seatbelt length.
No, they don't make those fatter. Man, have you guys flown Southwest before? Oh, it's my favorite airline. Huh? Nah, not for free baggage. Not even for the free baggage. It's because they're very pro-fat people. I'm on their list. So whenever because we fly fairly often, whenever we fly Southwest if we can. I'm already in their computer where I get an extra seat for free. And you know how you have to compete to get on the plane? You have to get in a line, right?
Yeah.
Not me.
Because
I get to pre-board because I'm fat. I get to get on the plane first, and I get a little card that I put on the seat next to me. It says reserved. You can't sit here. Okay?
That's good. I thought
So I'm just sitting there all chilling, never have to I get my bags on there, no problem. My wife gets to come with me as my caretaker. And I found out that, and this is like horrible too, when I flew from Milwaukee to Denver, that flight was overbooked. Okay. I had an extra seat. They were looking for volunteers. They bumped somebody off that flight so that I could have my extra fat guy seat.
Wow, they're generous.
I love Southwest. Great airline. They should all be like that.
As long as I'm getting how fat you are.
What happens? I mean, because now I'm on some pretty good thyroid meds, so I started losing weight. What happens if I fall off the list?
Yeah.
You got to decide. Do you got to bulk up before your trip to get your free seat, or maybe you just got to wear baggy clothes to make it look. It's like, no, I am fat. It's like you can just. Okay, so in any case, these guys are all data structures, right? Every one of them. So kind of throw this out of our mind that a data structure has to fit this certain mold. It's anything for holding crap. And all C++ did, it's kind of taking that step towards our object-oriented languages, is it said, you know what? We'd like to keep, actually, really C++ is similar to MVC. Okay, but it's almost the antithesis of it. MVC, that design pattern we talked about earlier, said, when you're designing an application, we should keep our designs over here and then keep the logic that makes that design work over here in two separate places. Okay? That way these guys don't get confused. Any of you ever worked in PHP before? Okay, so PHP, old PHP or new PHP? Did you use templates?
PHP 5.
Okay, so PHP, being one of our web languages, it was pre-MVC. And what you would do is when you were designing your website, you would have your HTML code in there, right?
Yeah.
And then you would embed PHP inside of the HTML code.
Mm-hmm.
Your logic, your design, same place.
Mm-hmm.
Bad. Okay? Not because it didn't work, but because if you had a PHP page that did anything, substantial, it became unwieldy, right? You had just a wall of HTML and PHP embedded in it, and it was hard to find what you needed to do. So that's why the fix for that was places started introducing templating engines. Okay, like Jinja is an example of one of these. So instead of you having your HTML and PHP in one place, you'd have your PHP in one place, and what it would do is it would just launch a template. That would be your HTML over in another file. It would bring it in there and then inject a couple of the pieces of information into it. So we basically jerry-rigged an older technology to do something new. That's why PHP is still popular. right? Nothing. I mean, so you've worked with PHP. What's good about PHP? I've made this argument that all these programming languages are the same. Why would somebody choose PHP over Java, for example?
I don't know. When I first had PHP after learning ASPX, it was open source, of course, on all platforms. I said, yeah, that works better. And works. I was a Linux person, so
Okay.
that's why.
So now when you play soccer, you wear soccer shoes, right? Soccer cleats? So why do you wear soccer cleats instead of ice skates? Oh, you could. It just wouldn't be as easy. I mean, I'll give you that. But you could run with ice skates. You look ridiculous. Okay? Because there are soccer players who play with ice skates, and those are hockey players, right? Isn't hockey basically soccer with ice skates? It's fairly similar.
Yeah.
I mean, there are a lot of similarities in the rules, right? Except there's more. Actually, there are more fights.
Yeah.
Why aren't there more fights in soccer? Like the soccer players don't fight that much. It's the fans that fight in soccer. Don't people get like trampled at these soccer games? I don't understand it. It's weird. What was I talking about? Oh, ice skates. Running in ice skates. All right. So we were asking why PHP?
Yeah.
Okay, well, you use cleats for soccer cleats, specifically soccer cleats. You don't use the football ones. They're shaped wrong, right? They don't give you the mobility. Football cleats kind of stick. Okay, they keep you from, they're meant for you to, shove up against somebody and not move. Okay, soccer cleats are meant for you to be nimble. You need to be able to change directions real quick, so they don't really dig in. They give you enough traction to let you do what you want to do, but not so much traction that you get stuck. All right, that's the point of soccer cleats. It's the right tool for the job. Okay, even though a soccer cleat, a football cleat, and an ice skate are all, quote, shoes. Okay, the right tool for soccer is a soccer cleat. Just like PHP, Java, C#, these guys are all programming languages. What is PHP the right tool for? Well, it's the right tool for doing a lot of web stuff because it was a language built with the web in mind. It has things built into it that make common web things easier. All right, just like those soccer shoes have the little nubby cleat things on it that make soccer moves easier. Okay, as opposed to using ice skates. Now, you could definitely play soccer and ice skates. It would not go well, but you could do it. It is possible, is what I'm saying. All right, so you could decide, look, I'm going to play soccer and ice skates, and that's that. So, same thing is true. You can write web pages in Java. You can write web pages in Python. You could write web pages in Scheme. So that would be a language that would not be bent towards making web pages, but you could certainly do it if you wanted to. Okay, it's just not made for that. It doesn't lend itself to that type of problem. It doesn't have power tools built into it to make that kind of problem easier. Okay, so when we solve problems, whenever we're working on an application, whether we're doing something in the IT field, where we're picking a piece of software that we need to install and configure, or we need to do something for a server, we're not necessarily, when somebody says, oh, what is the best? That sometimes, the correct answer to that is it matters. It depends, right? It depends on what's the best. Okay, if I ask you what's your favorite soccer cleat, or what's your favorite type of company who makes the ball, something like that, you have a preference, right? I don't know that much about soccer, but my guess is that certain pieces of equipment perform better in different weather conditions, stuff like that, right? So if you're somebody who's always playing out in hot and dry weather, there's probably certain pieces of equipment that are going to breathe more and stuff like that, so you don't just burn up. But I mean, if you're one of the Irish soccer players and you're playing in the mountains when it's 30 degrees and rainy, well, you might not want to wear that. You might want something that's a little bit less breathable and a little bit more survivable type thing. Okay, so the idea is that whenever we solve a problem, this gets back to what we were saying an hour ago. We need to solve that problem in terms of the tools we have available to us, and now we're going to add a piece to it, the constraints that are involved in the problem. Okay, so I've already put constraints on you in here where I said when you solve your homework assignments, you have to solve them in terms of the things we've introduced. Okay, that's a constraint. It's not going to be the most convenient thing in the world. Okay, but some of you who are already working in industry, you run into constraints constantly.
Yes.
Constantly. Okay? Sometimes you think it's stupid, but sometimes it's a good reason. Okay, I have a buddy, when I was just out in Denver, he's one of my former students from like 15 years ago or something like that. He he works for Lockheed Martin. They do aircraft and stuff like that. I think he does something with military contracts. I don't know. He couldn't talk about what he does, but it's probably far more boring than we imagine. But whatever, he does something for a place like that. Well, so when you're a military contractor, there's probably a whole lot of security type stuff, right? Well, whenever you start dealing with security on any sort of server environment, whether it's here on campus or your job when you're working with servers, you said you're a Linux guy, by definition, creating a secure environment is almost always less convenient than working within an insecure environment. Okay, so the second you need to make an environment secure, you've immediately put some handcuffs on your users. They can't do everything they might want to do. So now whenever you solve a problem in that ecosystem, the secure ecosystem, you have to take into consideration what can happen in that ecosystem without breaking your security, right? And sometimes the right tool isn't necessarily what somebody from the outside would say is the best tool. The right tool for you, or the right tool for my buddy who works for Lockheed, might be the tool that breaks their security the least, not necessarily the tool that's written the best or works the best. Okay, you're solving the problem within a set of constraints. All right, so these are always things we have to take into consideration when we're solving any kind of problem. Okay, so what did C++ do for us? It said, you know what? It would be a good idea for us to give you some sort of basket, some sort of thing that allows you to hold information about data as well as do things with that data and carry it around in one bag. Okay, rather than have them sitting in two separate places. That's a class. A class is a struct that also supports methods. All right? So the idea is that when we get a car is more than just a color and a material. Like, oh, I have a red car. Like, oh, well, does it move? Well, yes. Not before object-oriented languages it didn't. You'd have a car that is red over here, and then if you wanted it to move, you had to take that guy and throw him over to this guy and say, make him move. Go. Okay. Now we've thrown those things together into one place. All right? That's what object-oriented programming is. We're taking things that already existed, or just moved them nice and close together, throwing them inside a bag and saying, okay, now you can carry all that around in one little sack. Make sense? Okay. Just like this, we have a telephone and our email. Those used to be in two separate places. Okay? Now it's convenient. We carry it all around. Oh, also our video game system. Right? And also our other communication stuff, because we don't use telephones anymore, right? Telephones are stupid. Like literally, the phone could go out on my iPhone and I wouldn't notice. I probably make less than 20 minutes of phone calls per year. That's actually probably a lie. I probably make less than 20 minutes of phone calls to anybody except my mom per year. That's, but yeah. So I mean, with these things mirror what we do in real life, right? We're talking about these programming languages that seem maybe a little bit obscure and out there and difficult and stuff like that, but it's the same stuff we've been dealing with in real life. We talked about Tesla earlier. Did we need self-driving cars? Sure. How many of you are looking forward to the day when you can take a road trip and you can just get in the car and go and sleep in the back? Plug in the GPS coordinates, okay? Go in the back, watch Netflix, because now we have our internet with us everywhere we go, right? Until you fall asleep. That's going to be awesome. Okay, and I mean, and actually just think about what that's going to do to the travel industry when it comes to air travel. Okay, I mean, obviously you're going to still have, to go overseas, right? Okay, but I mean, I think you're going to, when you have cars that are truly self-driving, you're going to start seeing this whole new industry on like RVs and stuff like that. these big, basically driving homes.
Yeah.
I mean, now I don't have a house, I have an RV. Like, where are you going today? I don't know, I just dialed in something. Somebody wrote an app. It's a random destination roller. I just pushed the button and it just took me somewhere. I'll find out when we get there. Something like that. I mean, that's going to be awesome. Okay, but it's also going to change the way we think about travel. Right now, if you're going any place, air travel kind of becomes the first choice, right? Not because it's convenient, but because it's fast. Yeah, it's quick. If I were to drive to Denver, it would take a whole lot longer than the hour and 45 minutes I spent on an airplane with a nice, cozy, empty seat next to me. And right, so yeah, but the point is that I want to continue to make these analogies to real life and attach them to what we're dealing with in our technology, whether it's programming languages or what we run into in the IT world. We're constantly having new products that help us solve old problems in a better way. Okay? Everywhere we go. So don't put programming or IT or any of these technology things up on some sort of weird pedestal and say that, oh, well, that's hard. Where this other stuff just seems normal. So Tesla, self-driving cars, it's cool. I wouldn't pay that much money for it. Okay. If somebody handed you a self-driving car, you'd take it, right? So the point is, don't put programming languages up on a pedestal. We don't do it with real languages. So all of it, like I said, most of us speak more than one language in here, except me, right? I speak English and bad English and a little bit of Spanish, okay? I wouldn't even say I speak good English. I speak bad English and like a little bit of Spanish, and by a little bit, I mean like I probably can order at Taco Bell. But the point is that for most of you, you speak other languages, but the problem solving that goes in your head isn't different. When you're talking to me in English, or you're talking to your buddies in Urdu or whatever, right? You're still talking to a person. So what's going through your head is the same stuff, just the words you're spitting out, the syntax is a little bit different. Okay? Here we're talking to not a person, an alien computer. Okay? Whole different world for us, right? But it's good for us that the programming languages come and say, look, you can keep operating mostly like a person. And we'll handle the heavy lifting, that communication between you and the computer. All right? But the point is that we're not impressed by natural languages that might solve certain problems better than other problems, right? I don't know a whole lot about natural languages, but, I'm sure that there are languages on Earth that are more expressive for certain types of things than other languages, right? I think isn't French. French is supposed to be like a romantic language, right? So it's very expressive from that perspective, where, I think Russian probably doesn't do that well. Okay? So, we have certain languages that are more expressive. They're better tools for certain things than others, right? Some languages are, when they're sung, they sound more interesting than other languages. Some languages just don't sound like they should be sung. Like Chinese. Chinese probably should not be a sung language, right?
Why?
Well, it's a complex language. It's not that rhythmic.
Yeah.
Okay? Where like Spanish is a pretty good sung language. So the point is that Chinese, Spanish, English, these are all human languages. We can use them to communicate, but certain languages are meant for certain things or lend themselves to certain things, just like PHP kind of lends itself to web stuff. Java kind of lends itself to cross-platform desktop stuff. I guess that kind of stuff. Android, but that's going to go away. My prediction, we'll talk about it more when we get to the Android part of this, but just as Apple has moved away from Objective-C towards Swift on the iOS stuff, I think that Google is going to move away from Java towards their language called Go.
You said that last week,
Yep.
and I sent you a link about it.
Yep. That's right. Yeah. So it's and that's not. I don't think doesn't take a rocket scientist to see that. That's just the evolution of this stuff. There's nothing wrong with Java, but Java is an older language now. Okay. Java came out in like 1994, 1995, something like that. It's a lot newer than C. Okay. But it's not a young language, and the world of technology has changed so much since Java came out. that there's certainly improvements that we can make, right? So it's not so much that Go is inherently better than Java or that Swift is inherently better than Objective-C. You could still pull off all the stuff you need to pull off with either of those, but Swift has taken some things into consideration that might make your life a little bit easier as a programmer. That is, you spend more time writing the logic that matters in your code and less time writing extra stuff that you just always have to write because you do.
Yeah.
Okay? You know, it's kind of like Velcro instead of lacing up your shoes. But why didn't Velcro catch on better? How many of you have Velcro shoes? Why is that?
What is
Huh?
What
Velcro should be way easier.
Yeah.
Velcro, you know what Velcro is, right?
Yeah.
Yeah, man, that's like so much better. Why? When I was a kid, I had Velcro shoes.
Maybe it doesn't look fashion.
Is that it? So you think it's a fashion thing?
No, I say it's not. It doesn't look like.
That's what I mean. You think that we don't have Velcro shoes because it doesn't look fashionable? That's probably true.
Could be.
Yeah, I mean, I hate laces.
I have one.
I think
You have Velcro shoes?
Yeah, still
Aren't,
have it.
aren't they great?
Oh, very easy.
Yeah. I like Crocs. You don't even need Velcro.
you don't even need to touch.
Speaking of pets, I should just go in and have them like put the horseshoes on, just tack them on, just like you do for horses, right? Isn't that what they do with horses? They put horseshoes, they tack them onto their bottom of their hooves. All right, so class is our evolution of a data structure. Now we can put our fields, our attributes, the pieces of information we want to remember in the same place as the stuff that operates on it. Okay, so when we get back to this guy here, any object is a data structure. One's built into the languages, strings, arrays, the random object in Java. These are all data structures for holding information about strings or holding information about random pieces of information, that kind of stuff. And then the ones we build ourselves, the person object, the fraction object. These are all data structures, okay, for a very special kind of data. That makes sense? All right, so we're going to be talking about data structures, and here we're also going to be talking about algorithms. That's a kind of a scary word, right? Algorithms. What is an algorithm?
Step-by-step procedure.
Set of steps? All right, I like that. Maybe a recipe. So when we say, oh, it's a recipe for lasagna, that sounds less intimidating than an algorithm for lasagna. If you were going over to somebody's house for dinner and they were bragging about how they have a great algorithm or a great lasagna algorithm, that might make you a little nervous, right?
Wow.
You're not sure what this dude's
So
cooking with.
serious.
It's like, I have a lasagna algorithm. Got to try this. You know, it's maybe using some of the stuff that you guys put in your tea. Ay, ay, ay. No Chicago people this.
Oh yeah. What's Chicago?
Oh, you. Any of you live near
Sometimes I come from Chicago. I stay in Houston. Most of
you
the
stay in Houston?
I mean, I moved here in Houston.
So you're coming to school from Houston sometimes?
Sometimes.
Oh.
Sometimes I stay in Chicago also.
Huh? Portillo's. Did you hear they're getting one of those in Brookfield? A Portillo's? Yeah. Yeah, they're building one. I think it opens like in a couple of months. The Chicago place.
2 or 3 in Chicago, I think, Portillo's.
Oh, you got more than 2 or 3 Portillo's in Chicago. You got like 20 or 30 Portillo's in Chicago.
Yeah, the whole one Brockville, but it got closed like 2 years ago. I
No,
think.
it's just opening now. Yeah, they didn't have a Portillo's there. Food expert over here. If there was a Portillo anywhere within driving distance, like I have driven to Chicago for Portillo's. Just love Portillo's. It's so good. Yeah, so algorithms. These are basically recipes, right? It's a set of instructions for accomplishing something.
Set of rules.
Yeah, set of rules. When we're making lasagna, we're going to here's the stuff you need to make the lasagna. So these are the different pieces. Okay, so like a puzzle, like Legos, right? And then here's what you do with those pieces in order to accomplish a lasagna. Okay, no different than here's your Lego set that allows you to build the Batmobile. Okay, same thing. You have a recipe, you have an algorithm for taking all these different color pieces that are in different shapes, and you follow the little number thing and say, oh, I put this piece here and this piece here, and oh, I got a Batmobile. Okay, Batman could ride in this if he was a lot smaller than he usually is. All right, so that's what an algorithm is. It's a recipe for stuff, set of instructions, whatever. Okay. All right, now, what kinds of things do we have algorithms for?
For any problem.
Anything. Literally anything. Okay. So do we have an algorithm for walking?
Yeah.
Sure. Tell me about your walking algorithm. What goes through your head? I mean, I assume you study it before you get out of the car because, I mean, you don't want to fall, right? We don't do that, right? We already talked about how complex walking is. So certainly somewhere inside of that thick skull of yours, you got an algorithm for walking, right?
Yeah.
Okay. But you never review it, do you?
Never.
I guess it's all about
If you're a cook and you've made a lasagna 1,000 times, could you probably make that lasagna without looking at the recipe? Sure. I mean, it's just like me and like Campbell's soup. I'm pretty good at grilling. I have like a second, I don't know, 9th, 10th, 11th sense for when the steak is done to the right level. But I like really like crusty, so I literally light the steak on fire. Well, I don't like it well done. I want it like medium rare, but I want it to have a really good char on the outside. So you have to light the meat on fire and let it burn until it's cooked inside but charred on the outside. It's a skill.
Is that lasagna?
I don't make lasagna that way. You do not want to light lasagna on fire. Okay. So, in any case, we when we do something multiple times, we become so accustomed to it that we don't need that set of instructions anymore, right? Okay. So we can apply algorithms or recipes. These are synonyms. We can apply them to anything. Anything. How do we brush our teeth? How do we feed ourselves, right? Okay. How do we go to sleep? We all have an algorithm for going to sleep. And that might not be the same, right? Some of us go to sleep laying on our back. Some of us roll on our right side. Some of us roll on our left side. Some of us roll on different sides at different times of the night, right? Okay. We have our own little rituals that we do for these different things. Okay. They're all ultimately accomplishing sleep, just like there's 5 million different lasagna recipes. Okay. Still a lasagna. Some of them might taste a little bit better than other ones, but that's still in the eye of the beholder because, hey, if I make a beef lasagna and you don't like beef, you're probably not going to like my lasagna. Okay? You make a tofu lasagna, I'm going to laugh at you.
I have never tried. Maybe I can try.
What, tofu lasagna? The only way to eat tofu is when you fry it and put pork in it.
I will let my mom try and ask you to test it.
She used a lot of tofu. I mean, I like tofu, but it's like, seems like a cop-out. Less so, though, than turkey bacon. Turkey bacon shouldn't happen. It's not a thing.
How about turkey sausage?
Turkey sausage is almost as bad, but turkey bacon,
It's more terrible.
yeah, I mean, that's just ridiculous. It's just absolutely ridiculous. Anyway, I get that there are cultures and different belief systems where you don't eat pork and stuff like that. I can respect that. Don't try to fake it, okay? It's like, oh, well, I don't eat pork, so I eat turkey. I eat turkey bacon. No, you don't. That's not a food, right? Okay, you're just giving up bacon is what you're doing. What you're eating there is not food. It's something else. Something that shouldn't exist is what it is.
Beef bacon?
Beef bacon is surprisingly better than it should be, but I don't think it's better than turkey bacon, but it's not pork bacon. It's not pork bacon. So yeah, the beef bacon, that's what my relatives are all like Orthodox Jews, like,
They don't eat
oh, they don't eat pork.
pork.
Yeah, no, they don't use electricity at certain times of the week and stuff. Yeah, I mean, it's strict. I couldn't live without bacon. It's the best way to convert Jews to Christianity is just hang out outside the how to hang out outside the synagogue with cooked bacon. Start handing that out.
Or you can have a Reuben sandwich. That's like bacon.
That's corned beef.
Yeah, but it's really tasty.
No, I love Reubens, but that's not bacon. I mean, they're not comparable. Corned beef's not trying to be bacon. I like corned beef. Corned beef is legit. Yeah, so, but
What
that's
is the relation between algorithm and data structure?
and bacon.
I mean,
Bacon is related to everything.
Okay, so what is the relation?
What's the relationship between algorithms and data structures? Okay, so when we talk about so let's stay with this food example then. So we talk about a recipe for making lasagna. Well, we also have special structures, pans or whatever, that allow us. So maybe a cheesecake is actually a good thing. So when you cook cheesecakes, a common way to cook a cheesecake is in inside a spring. I think it's called a spring pan, something like that, where it holds its shape, but when you go to take it out, you pop it so the pan goes wider to release the cake. Okay, so you have a specialized structure that you store the food in during the preparation, and then at the end, it makes it easier to remove. Otherwise, you end up destroying the cheesecake, taking it out of the pan. Okay, so these guys kind of go hand in hand. We apply algorithms to problems, and sometimes those problems are going to involve, well, almost always the problems will involve a data structure of some type. Those data structures are going to come in some different flavors and that kind of stuff. Okay, so they tend to go hand in hand. In fact, most of the time you'll find data structures books are called data structures and algorithms, or they'll have a chapter or a section of the book called algorithms that just kind of talk about some common ways of using data structures. So, for instance, one of the things we're going to talk about in here is something called an AVL tree. So an AVL tree is a self-balancing tree. So we're going to be looking at an algorithm that allows you to rebalance a tree. So it's a recipe that you apply to a tree data structure. It's a binary tree data structure. You apply this recipe to it to make sure that data structure always stays in balance, whatever that means. Okay, so they do go hand in hand from that perspective. But again, algorithms are a very generic term, even though they sound scary. Okay, we have an algorithm for walking, algorithm for making lasagna, an algorithm for making lemonade. Okay, an algorithm for sleeping, algorithm for tying our shoes. We can just keep going and going, right? And then if we want to come up with, we want to be really special and start getting publications, we create design patterns around our algorithm. But if you name it something arbitrary enough, you might even be able to get a computer science paper published where it's a design pattern for making a lasagna. Okay? But if you talk about it in an abstract enough way, since most people don't read these anyways, right? You might actually be able to get a publication that's about making lasagna in like a computer science journal.
Maybe.
That would be like a funny challenge. You just talk about a really high level, like,
That's really hard.
you refer to cheese as, it's like, it's the binary cheese, but you spell it kind of weird. And okay, so in any case, those are some of the things that we're going to be talking about. So as we kind of dive in here, what I'm going to do is I'm going to kind of start introducing something. Typically, I'll go close to 2 hours until we're at a breaking point. Then we'll take like a 30-second break. And usually about a 10, 15-minute break tops. And then we come back and we go. I like to say I try to get you out a little bit early, but that rarely happens. I usually keep cooking until 10. I think maybe some of your other classes, they're letting you out like at 7 or 8.
That's really, I guess 8 is
8?
quite common.
Don't you feel like you're getting ripped off if you're only getting 2 hours out of your 4-hour class?
That's true.
Yeah. Depends on. I mean, for example, your class.
It's interesting, so you don't want to
2
escape.
hours, yeah, you just want to listen.
Another class, you're dying to get out of there 10 minutes in. Like with Dr. Locklear?
I guess not. I like this.
By the way, I record all my lectures, so you can go back and watch this and listen.
I will tell Taffia to read this, what you said.
Well, that's fine. I think he actually talks about me in several of his classes. I think he's quite aware that I'm more entertaining.
Summer 501.
Okay. I made the lecture.
No, he mentioned you in some technology that you use it in a very different way. You try clubbing one with the other and messing up with the technology.
Oh, I see. Yeah, he's weird.
Give you an example.
He's weird. He's old. Yeah, we're at hour 39 minutes in case you guys want to pull out those pieces and email it to him. I've known Gary for a long time. He is older than me though. It's like I could be one of his kids.
You've been working here for 10 years?
I've been here 10 years. And then I was at Western Illinois for 7 years before that. I could literally be one of his kids. I would be like his oldest kid, but I could, like, on paper, I could be his kid. That's old.
It's not. It's because everyone is in the department.
Well, actually, you know one of his, Professor Josh Locklear. Yeah, Professor Locklear. He's that's Dr. Locklear's oldest kid. Yep.
So how old is he?
36?
Really?
Yeah.
So you can be his kid.
Yeah, I'm older than he is, but it's not by much. All right, so in any case, let's start talking about I'll probably go about another 10 minutes or so, leading us in to linked lists. Then we'll take a little break, and then we'll come back and we'll dive into linked lists. So what we want to do is we kind of want to talk about the original quote data structure. Okay, so the original data structure. So right off the bat, what we want to think about when we've kind of arbitrarily talked about data structures in here, but we want to think about data structures as containers for holding stuff. That's what they are, right? When we're solving problems, we're working with data, and data structures are there to make our life easier. Okay, so our original data structure that's pretty much built into every language is an array. Okay, so an array. And we saw this in our evolution of C and C++, and it's going to be there in all these different languages. Some languages call them lists or something, but they're all the same thing. What's an array? It's a collection of crap. Well, let's see. Let's say a collection of like data stored within a single variable name. Okay, it's a big container that we can throw crap in. My shoe bench. Okay, my shoe bench is an array. It's got predefined cubby holes that hold shoes. And you stick shoes in there, and you can't put more than one shoe inside each cubby hole. At least not my shoes. I have very big shoes. Okay? My wife has little shoes. You might be able to stick two of hers in there. But I have a pocket wife.
Does that array should be a linear?
I would say that's true. So arrays, we can say, are definitely linear structures. Okay? Linear means that we hold a bunch of stuff in a line. We don't have branches hanging off of it. Okay? So, as an example, whenever we form a line for something, when you go to McDonald's, okay, the appropriate organization for waiting in line at McDonald's is a line. Really, for us, it's a queue, right? You get in the end of the line, you come out the front of the line. So it's a special kind of linear data structure, is a line or a queue, but it's a linear data structure. Okay? We get into a linear format when we're waiting for our food at McDonald's, as opposed to a non-linear format where you have one person trying to order and everybody else is just in this crowded mass behind them, where we don't know who's next. Okay? That's what happens at the soccer games. Right? Yeah, the soccer games. That's why people get killed and trampled and stuff like that in the soccer games. All right, so punchline is that it becomes the right tool for the job. Linear data structures allow us to hold one thing after another. So they rely on us putting things in at one point, taking things out at another point, okay, rather than things existing in a big crowd. We'll talk about nonlinear data structures as well. All right, so fair to say arrays are linear, relatively unimportant for our understanding. But we want to talk about kind of the pros and cons of arrays. We want to review arrays a little bit because And one thing I'll just say right now, related to arrays, is these are not bad. So when we introduce linked lists, it's easy to say, oh, linked lists are the upgrade for arrays. They're not. It's just another tool in our arsenal that we will use sometimes when it makes sense, and we'll use arrays other times when it makes sense. Okay? So let's talk about pros and cons of arrays. First, let's look at an array. We'll just build a little array here in Java. So we'll say int array AR is equal to a new int array size 5. All right? So there's a line of code that's going to generate something for us. That's going to generate an array for us. And that array is going to look something like this guy. All right, so we'll say this is 0, 1, 2, 3, 4. Okay, so when we create this, it's going to generate for us a variable named AR, and AR is going to hold a value. The value of AR I'm going to say in this case is actually 100. AR does not hold an array. AR holds a memory address. It's a memory address that points to a place in memory where that array lives. Okay? Now, just real quick, let me just prove this to you. We'll pop over here to Eclipse. Most of you have seen this before, but we'll just do it anyways. Let me just close all this stuff. So I'll go ahead and create a new project. Let's call this CSC537 Fall 2015 linked list. So we'll add to it here in a few minutes, but I'll just use it as our starting point. So I'll create a class in here just called driver real quick. All right, so I'll go ahead and create my int array AR as a new int array 5, and then I'll do a system.out.println AR. And we're going to see that this prints out a memory address. Creepy looking memory address. Not something that looks like this. All right, so AR is a variable that holds the address where our array lives in memory. So to kind of paint that picture, we're going to put a 100 in there. I'm going to put a, I know you can't see it yet, but you will. I'm like a keynote savant. All right, so these are the memory addresses, 100, 104, 108, 112, 116. These are the corresponding buckets. This is bucket 0, bucket 1, bucket 2, bucket 3, bucket 4. Notice the value of AR. The value of AR in this case is 100. That is, it points. This guy is a pointer, and he points to the beginning of the array in memory. All right? So one thing that's going to be incredibly important for us in here is this idea of a pointer. This is a primitive type variable capable of holding a memory address. Okay? So those of you who have dealt with C or C++, languages that are very memory dependent, so one of the things that Java has done for us as we keep walking forward, kind of the evolution of Java, is they have taken away some of the things that we used to have to deal with in C and C++. As a C and C++ programmer, we had to be very aware of the memory we created and then get rid of the memory when we were done with it and all this stuff. Java has said, you know what? Those are things that, yes, it was important. Yes, you had to do it. And yes, it's still happening. But maybe we want our cars to have automatic transmissions. Okay, so I'm making some of these analogies. Okay, how many of you drive a stick shift now? How many of you know how to drive a stick shift? It's fun, for like 15, 20 minutes, right? Until you want to go and take a sip of coffee. Okay, I remember years ago, I wanted a stick shift because it's fun. It's like a video game,
Yeah.
right? For a small period of time. Then you kind of want your automatic transmission so you can just go. All right, so, punchline is that what's Java? Java's kind of like an automatic transmission. It's not that it's any more or less capable than C++ in the big scheme of things. It's that C++ had a manual transmission with stick shift. Java is an automatic transmission. Okay? It does a lot of the stuff for us so that we don't have to. It doesn't mean that that stuff's not still happening. Okay, and that's an important thing because what ends up happening in a lot of the textbooks, and I gave you in the course, I gave you a Java book that I won't use it, but if you want to have a book for reference, you can look at it so you don't have to buy anything. So hopefully nobody bought a book for this class. Yeah, I don't do books. I know more than they do. So it's. Don't you hate that when you come to school and you got to spend $800 on books? Just dumb. All right, so anyways, these pointers, a lot of Java textbooks say pointers don't exist in Java. Okay? That is a pointer. That exists in Java. This is Java. Okay, so, okay, so I don't want to alarm anybody here, but if you were taught that pointers don't exist in Java, you were taught wrong. Okay, the reality is it's not that pointers don't exist in Java, it's that Java lacks a specific syntax for working with memory. All right, we definitely still store memory. We just proved it. We created an array. We printed out the value of that array. It's clearly a memory address, okay? But we don't have the specialized syntax like in C and C++. We had the asterisk for getting out a memory or getting the value at a memory address. We had the ampersand for getting the memory address of something. So we had special syntaxes for working directly with those things. We just don't have that extra little tool here in Java. All right, the engine is sealed. We can't get in there with the wrench and start changing stuff. Was it Honda? Honda makes the sealed engines, I think. Pretty sure. I think Honda race cars, that's their thing. It's that, you can't fix the engine. It's a sealed thing. Okay? Engine's still there, still does cool stuff, still generates all the horsepower and all that stuff, but you can't fix it. Okay? Just like an iPhone. Battery's in there, we can't change it. Take it in, they give you a new phone. Right? Except I think there's some people that know how to open it up and then it voids your warranty. Just don't tell Apple. All right. So in any case, pointers, incredibly important. In fact, we're going to be operating almost solely on pointers in this entire course. Okay? And it's going to be intimidating at first. When we start drawing these pictures, we're going to have things that point all over memory, point all over the place. And it's going to put us in an uncomfortable situation. Because we're not used to that. We're not used to having to think about memory. Those of you who came from older languages like C and C++ are going to be at an advantage when you start thinking about our data structures because you're going to be not thinking about them through a foreign lens. You're used to, at some level, seeing memory. Okay? This can be intimidating if you start seeing things like that printed out to the screen. All right? No different than if you're, most of us in here are probably Windows users, right? Okay. So you get the blue screen of death, right? Okay, blue screen of death, what happens? You get this just the wall of blue stuff with all the weird memory address and stuff like that. How many of you try to read that and you just say, oh, something broke, let's reset? That's what we do, right? Something's broken. This looks like alien gibberish to me. I'm not going to try to read it. Okay, but those are all memory addresses and stuff like that. Okay, they are meaningful, they are important, But for most problems that we solve, we don't need to deal directly with memory. Okay? So just to kind of give us our initial punchline here, give me about another minute or two and then we'll take a break, is here's what an array looks like. All right? When we build an array called AR and we set it equal to be a structure for holding 5 integers, that builds something that looks like this for me. Okay? For human convenience, we can index through this guy. This is bucket 0, this is bucket 1, this is bucket 2, so on and so forth. But bucket 0 actually lives at memory address 100. Bucket 1 actually lives at memory address 104, so on and so forth. How did we get that? Well, if I say AR at bucket 1, that's the same thing as saying AR plus 1 times size of int, because this is an integer array. And what does that mean? Well, AR has a base address of 100 plus 1 times size of int, which is 4 bytes, 32 bits. So that gives us 104. Bucket 1 lives at memory address 104. Bucket 2 108, right there. Bucket 0, 0 times 4, it's going to be 0, so 100 plus 0 is 100. All right? That one fact, so we understand that little math we just did there? That one fact is both the greatest strength and the greatest weakness of arrays. All right? So let's just get that out there and then we'll take our break. So arrays, strength, fast. Why are they fast? Because we can mathematically compute the various locations in it. I can just go directly to bucket 3, okay? Because I can mathematically calculate where in memory bucket 3 is if I know where the beginning of the array is. It's an offset off that. I don't have to walk from bucket to bucket to bucket. I can just go there. So it's fast. In the same vein, though, weakness. Memory inefficient. To create an array capable of holding 5 integers, I had to find a chunk of memory big enough to hold 20 bytes. Each integer is 4 bytes. So 5 times 4 is 20. I needed to find a chunk of memory capable of holding 20 bytes right next to each other. Otherwise, our little math trick won't work. Okay? All of those buckets have to be sitting right next to each other. We built a 5-bucket array. How big's 20 bytes? Not that big. But we can certainly imagine that the bigger the array we create, the more memory we have to have right next to each other. Right? Okay? But the problem with arrays then are that once we create them, it's a structure that's there. So we take our parking garage out here at Concordia, right? So we built that parking garage. It has a certain footprint. What if we wanted to add 100 more parking spots to it? We have to get more land, right? So in computer science perspective, if you want to have an array that holds 10 things, then you want to make it hold 20, you got to knock down the old array, knock down the old parking garage, build a brand new one that's twice as big on a plot of land that's twice as big. That may not be the original plot of land. Make sense? Okay, so arrays, really, really, really fast, very memory inefficient, okay, because they are fixed in size and they require everything to be right next to each other. Now keep in mind that that's neither bad or good in the big scheme of things. A little bit ago I mentioned that arrays are not bad. If you need something to be very fast and you know exactly how many things you need to hold and that number of things isn't some astronomical number, arrays are great. Why wouldn't we want it to be fast as long as we have enough memory to hold it? Okay? But when we start getting into collections of things that have to hold arbitrary numbers of data, do you hold 5 things or 10 things or 30 things or 80 things or 1,000 things? Who knows how many things we're going to have to hold? And it's going to keep changing over time. We don't want to have to keep knocking down that parking garage. You want to be able to quickly expand that parking garage. Add another parking spot as you need one. Okay? Well, to build in that functionality is going to come up with a cost. That cost is going to be slowness, relative slowness. Okay, so let me just create our next slide here that we'll start off with. We're going to start talking about linked lists. And we'll go ahead, let's take about a 15-minute break. We'll come back at 8:20. I'll go ahead and get this video uploaded. I usually do the videos in two segments. And I'll put up the link to the videos. But so 8:20, 15 minutes.